Okay, in this video, we're going to look at Newton's second law and eventually leading us on to the ideas of impulse. Now, Newton's second law is an interesting one because it's often peddled as this: F is equal to m times a, and that is very much correct. There's nothing wrong with that, but in terms of what you're expected to do, you're expected to define it slightly differently. Newton's second law is the resultant force, this resultant force right here, that acts on an object when there is a rate of change of momentum. I'll say that again. There's a rate of change of momentum. Now you might be asking yourself, well, where is the momentum in this equation? Because there's m and there's a, there's no v. But we can actually have a look at a and realize that a is something quite profound, from a little bit of Suvat maybe. Well, a is the rate of change of velocity. So we can actually define a over here as the change in velocity over the change in time. And actually that is very useful because what we can then do is we can suggest that force is equal to m delta v, so that's change in velocity, over the change in time. Well, we might be starting to, the more savvy amongst you, we might start to see that this value at the top here is essentially a momentum calculation, mv, but with a delta v, it means it's change in momentum. So we can change this calculation to read change in momentum is over the change in time. And that is very, very helpful. And that is equal to the force. And that is your Newton's second law, that the force on an object is directly proportional to the rate of change of momentum. Okay, I'll say that again. The net force on an object is equal to the rate of change of momentum, and that's going to be really, really useful later on. Okay, now, so impulse. What is impulse? Well, impulse is just a rearrangement of that previous equation that we looked at. So we had F is equal to delta rho over delta t. So that's change in momentum over change in time. And so what we have here is a situation where we can rearrange this equation to read something slightly different. I'm going to read it like this. F delta t is equal to change delta rho. I'm just going to make my rows a bit more slanty than they are, just to make sure that you get the idea that it's not a P. So, and what we've done here is essentially we have demonstrated impulse. This value here is the impulse of an object, okay, or the impulse of a collision. So when we're looking at impulse of a collision or the impulse of a force, we can work out the amount of time it takes for this collision to happen, and we'll do some examples shortly. But this is impulse. Now, we've already introduced a unit of momentum to you as kilogram meters per second. But from this equation, hopefully you'll be realizing that there's another unit that change in momentum could be. So even though change in momentum is the same as momentum, impulse technically has the same unit, but it also could be Newton seconds, because of force is in newtons, time is in seconds. So we can have two units for impulse. The more common one is the Newton seconds one. So when we're looking at this, so that's the impulse there. Now, impulse has a very, very useful concept, and actually is used very widely in sports, ideas around sports, and we'll talk a little bit more about those when we get into class about a baseball thrower, a cricket catcher, and the implications for this equation are very profound in sport very specifically. So we'll look in a second at how we might utilise these graphically on the next slide. Okay, so looking graphically at how we might utilise this impulse idea is, say for example, we've got a force time graph and we get a object that has a constant force acting on it, and then that force drops off at this point here to 0. So you might suggest that this could be a car accelerating. This is its resultant force right here. and at this point it's no longer accelerating, it could be moving at a constant speed. So that's a nice example of that. So how do we use this? Now, essentially, because that force is exerted over a time period, or a change in time, because it's gone from time 0 to time whatever that is, then that means that we've got F, we've got a delta T. Well, where have we seen that before? Well, we've seen that that's impulse. And if we look here, the area under the graph then is equal to the impulse. So the area under a force time graph is equal to the impulse. Now, as we saw in the previous slide, impulse is equal to the change in momentum. And change in momentum for most objects, they don't generally change mass. So the only thing that does change is the velocity. So this is quite nice, because what we can say is that the impulse divided by the mass will equal a change in velocity. Please note that is a change in velocity, not a final velocity. So, for example, suggesting that this object starts from 0 meters per second, and let's just throw some random numbers in there just to make this interesting. If we suggest that the impulse is 1 and the mass is 2, then what we'd expect is a change in velocity of 0.5. So, and that's meters per second, so over that time in which that force is acting, by the time it gets to there, what we'd expect is that the change in velocity to be 0.5. Now, assuming that this is a car accelerating, then we would expect it to be 0.5 meters per second as a final velocity. What happens though if we change this up slightly and we suggest that it already had a starting velocity? Say it was starting at 2 meters per second. Then over the course of this force acting, we've got a change in velocity of 0.5, so the final velocity will be 2.5. Let's propose another scenario. Let's propose that instead of this force being an accelerating force, it is a decelerating force, a force that acts opposite to the direction of motion. Then over the course of that time, since the force has acted opposite, what we'd end up with is a final velocity of 1.5 meters per second. Because remember, velocities are a vector. Forces are vectors, and they can act opposite to the direction of motion. And you've got to watch out for that to help you see whether or not the final velocity is going to be less than or more than the original position. Now, there are extenuating circumstances as well. Say, for example, let's just put this in context. It's using the same numbers, or similar concept even. So let's say the starting velocity is 0.25 meters per second. Okay, I'm keeping the numbers simple on purpose, just to make sure you're happy with it. So 0.25 meters per second is the starting velocity. Now let's suggest that this is the decelerating force, as we just suggested in the previous question. So we've got a negative change in velocity. So that means that if you look at on a number line, so let's look at this on a number line. So there's 0. There's where I am right now at 0.25. So if I change it by minus 0.25, then essentially what I'm doing is I'm taking it past the 0 into the minus numbers. And as you'd hopefully expect, a change of 0.5 would lead me to minus 0.25. Now, what does that minus 0.25 mean? Well, it means that the object, as a result of this impact, has changed direction. and it's going in the negative direction now. And that's something you've definitely got to be wondering about. And pretty much the examples that you'll see will give you plenty of experience and practice of this, but you do need to be aware. Think of it as a number line. So change is 0.5 in this case. It was starting at 0.25. We know it's a decelerating force, so it's causing opposite to direction of motion. So we end up with it travelling in the opposite direction as a result of that impact or as a result of that force.